welcome to homework for part 2. In this part of the homework, we're going to start taking a look at the controls of certain processes. And what we're asked to do here, one of the first things we're asked to do here is take a look at a PID controller. So this is the output of our PID controller. We have our KC, and then all multiplied by the error, plus 1 over tau I. Integrate the error from 0 to time. And then we add on tau d and the derivative change of the error with respect to time. And what we're asked to do is we're asked to find the transfer function of this PID controller. So if we go ahead and do that and do the Laplace transform, what we'll find, and I'm just going to call this P, the output of our PID controller. We'll have KC, right? And then doing Laplace transform, we'll have our error. I'm going to write our error as E instead of epsilon, just easier to write for me. And then we'll have 1 over S, right, because we're integrating. So we'll have E over tau I S. And then adding on tau d, Laplace transform of the derivative is just S, and then E, right? So now what we can do is we can go ahead and simplify this down a little bit further. So I'm going to pull out our error here. So we'll have KC, all multiplied by 1 plus 1 over tau I S plus tau d S. And then this is all multiplied by E, right? So essentially what we have here is we have our transfer function here that relates the error to our the output of the PID. So what we can do here is we can actually break this down a little bit further. So we'll have KC times, if we do a common denominator here, we'll have tau IS on the bottom, tau IS on the top, right? And then plus 1, and then plus tau I S squared tau D, right? And then this is all multiplied by the error. So this here is our transfer function of a PID controller. So what we're going to look at now is a process control loop here. Essentially what we have is 2 tanks, and what we have here is Q, the flow rate that is going into our first tank. It then goes into a transfer function which outputs us the height of the first tank, right? Then which goes into a transfer function again to give us the flow rate out of that first tank, so Q2. Then this goes into a third transfer function here that outputs us the height of the second tank. So we have one tank that is flowing into another tank, and the first tank is being filled by Q. So what we have here is we have our desired output, H2, the height of the second tank. And what we're going to do is we're going to take this value of H2, and usually what happens in process control loops like this is you take it through some measurement device to get your output in either meters or feet or whatever desired unit you're looking for. But we're just going to say here that our output is already in our desired unit, and we're just going to multiply H2 by 1 here. So essentially this is our measurement device, but we're not going to use it. So out of here, we still have our H2. And then what happens in this loop is we take our H2 here, and we have our height set point that we have specified. And what we get to a point here where we have our comparator, basically comparing what we have specified as our set point to what our actual height is, and it then basically gives us an output that is either plus or minus what our set point is. And we know this to be our error, right? So this is our error. And what's useful about deriving that PID transfer function is that in a system like this, what we would do with our error is then we would put it into our PID transfer function, right? And then close the loop, right, to our flow rate. So essentially we're correcting here to be able to get our height to the set point. So very useful here to be able to use our PID transfer function. And we're actually going to take a look at a few problems down the road that utilize control loops like this. So obviously what we need to be able to learn how to do is to multiply polynomials here. So what we're going to go ahead and do is go into Python and learn how to multiply these polynomials first so that we can solve these types of problems for control loops. So let's go ahead and do that. Okay, so now that we're in Python, what we're going to go ahead and do first is I'm just going to show how we can multiply polynomials here in Python. So it's a big help not having to multiply these transfer functions by hand. So what I've gone ahead and imported here is from numpy.polynomial, I've imported polynomial as p. So essentially what we can do is specify our polynomials as p, and then we supply the coefficients of the polynomials in increasing order, and then we can multiply them. So what I mean by that is if I have a polynomial of 1, 2, 3, and I just go ahead and press Shift Enter, what this means is that this polynomial is 1 plus 2x plus 3x squared. So that's what I mean when I say the coefficients are in increasing order. So what we can do here is we can go ahead and we can say, okay, we're going to take this polynomial and we're going to multiply it by a polynomial with 2 and then 3 as the coefficients. So this would be 2 plus 3x, right? And we're going to go ahead and multiply these. So Shift Enter. And then this is the polynomial that we are returned as our result. So that's how we multiply polynomials in Python. Okay, so before we start multiplying transfer functions, we've run into a bit of an issue, and that issue is because in Python, for polynomials, it asks us to supply the coefficients in increasing order. However, when we go to use the transfer function library, it asks us to supply the coefficients in descending order. So essentially what I'm going to do to basically combat that discrepancy is to set up a couple functions here to basically translate a transfer function to a polynomial in terms of, or the numerator and denominator in terms of a polynomial, and then also taking a polynomial with a numerator and denominator and then translating that into a transfer function. So I'm going to go ahead and define a function here, and I'm going to call that transfer function to polynomial. And what this is going to do is it's going to accept a transfer function, so TF, and then what we want to return, so return, and I'm going to return our polynomial p that we have created up here, and it's going to return the numerator of the transfer function. And what we need to do is basically take the order that is in and completely reverse the coefficients. So if I go something like colon, colon, -1, that colon, colon will read the entire array of the numerator, and then the -1 will basically flip it in reverse. So I'll do that for the numerator, and then likewise for the denominator. So again, grabbing the denominator, den, and we will read it in reverse. So now we have returned a polynomial that will return our numerator or have our numerator and denominator flipped in the right way. After this, what I'm going to do is likewise set up a function that allows us to translate a polynomial with a numerator and denominator into a transfer function. So I'm going to go define poly to transfer function, and this is going to accept a numerator and denominator from the polynomial. So I'll call that n and d. And then what this is going to return is our transfer function, and we'll have n dot coefficient, and then we'll go ahead and reverse that order of the coefficients. So we'll go colon colon -1, which will return us the reverse order. And then likewise for the denominator, we'll go transfer function d dot coefficient, and the same deal, we'll go ahead and reverse the order of those coefficients. So colon colon, read the whole thing, and then reverse it. Okay, so basically we need to be able to do this because we're going to in a minute here have to multiply transfer functions in that control loop that we have. Okay, so now what I'm going to go ahead and do is define a function that will allow us to multiply transfer functions. So I'm going to go define tf mult for transfer function multiply. And what this will accept is then two transfer functions. So we'll go tf1 and tf2. And then what we're going to do from here is we'll get our numerator of the transfer function 1 and the denominator of the first transfer function. And we're going to take those as transfer functions and get those to polynomials to be able to multiply them. So tf2 polynomial, tf1. And then likewise for our second transfer function, I'll just write it out here, n2, d2, again taking it from a transfer function to a polynomial to be able to multiply. And then what we will return here is our transfer function, and what we'll have here, or actually excuse me, what we'll want to return is we'll have multiply the numerators and then the denominators, right? So n1 times n2, and then multiply our denominators d1, d2. So it will return the numerator and the denominators multiplied. And then what we'll want to do is take that from a polynomial back to a transfer function. So we'll go poly to transfer function. Okay. So now we have our function to be able to multiply transfer functions. And now what we're going to need to do, if you go and look back at the control loop, is we need to code in our transfer function for the PID controller that we have. So I'm going to define a function. I'm going to call it PID. And in order to return our transfer function, what we need to have is our KC, tau D, and tau I. Forgot my colon here. And then what we'll need to return here, for our numerator. I'll have a transfer function. But for our numerator, what we'll have for the highest power is KC. If you go back and look at where we did common denominator and finally we got down to our final transfer function for the PID, we had our highest order, which was KC times tau I times tau D, and that was multiplied by S squared, so which was our highest order. So KC times tau D times tau I. Our first order was just KC times tau I. This is all our numerator here. And then we had the 1 in there, which will just be KC multiplied by 1. And then for our denominator, we had KC, I'm trying to remember here. Yeah, we had tau I, excuse me, not KC, just tau I times S in the denominator, so we have tau I. And then we also need to supply our lowest like constant at the end. And since we don't have anything in the denominator, we'll just supply a 0, basically putting it as plus 0. So let me make sure this matches up. So yeah, so we have our function here for our PID in terms of a transfer function. Okay, so I think we're ready to go ahead and look back at our control loop and multiply those transfer functions and then multiply that by our PID controller. So if we go back and look at our control loop, I'm going to basically take two of our transfer functions and multiply them here. So I'm going to create a variable called QC. So basically from our controller, the PID, to our flow into the first tank, QC to Q2, which is the flow of the second tank. And then for this, we're going to create the transfer function. So what it wants us to supply here is the numerators, or the numerator and then the denominator. And if you go back and look at this, we can cancel out the r's. So in the denominator, or in the numerator, what we're just going to have is 1. And then in the denominator, we have a1 times r1 and then plus 1. So we'll have a1 times r1 and then comma 1. And then for our second transfer function, we have q2 to our output, h2. So q2 to h2. And for this transfer function in the numerator, I believe we had r2. And then in the denominator, we had a2 times r2 and then plus 1 again. So a2, r2, comma 1. And what we need to go ahead and do here is define a1, r1, a2, and then r2. So let's go ahead and do that. So we'll put a1 is equal to 1, r1 is equal to 2, a2 is equal to 1, and then r2 is equal to 2. Okay. Now what we can do, since we have our function tf mult, we can go ahead and multiply these transfer functions together. And then from there, the last transfer function we have in the forward direction of our control loop is our PID transfer function. But let's go ahead and multiply these two transfer functions together first. So we'll go tf mult, and we'll have our transfer function qc to q2. And then what we want to multiply that by is q2 to h2. And looks like we have an error here. And yeah, actually I forgot. Somewhere up here, I believe I made an error in parentheses. It didn't show up, but something wasn't right up here. Here it is. So when we go from our polynomial to our transfer function, we just want to return just one transfer function here. So I'm going to get rid of this parentheses here and this TF and open parentheses here. So we just have our numerator and denominator here, and that should be able to fix our issue here. See if it does. Yeah, so we were able to multiply here. Oh, I forgot to multiply this. A2 times R2. So this gives us the transfer function that is returned from multiplying these two transfer functions. And then if you look back at our control loop, what we have left in the forward direction of the loop is to take these two and then multiply that by the PID transfer function. So if we go tf mult, we have our PID. We'll need kc, tau I, and tau d. Okay, and then we have a comma there, and then we want to multiply these two together. And we'll close our parentheses, and I just need to supply our kc, tau I, and tau d. For kc, I'm just going to put that as 1. Tau I, will put that as like 10, and then tau d, we'll put that as 0.1. So let's go ahead and run this and see if it works here. So it does work here, but let me see. I believe
this wasn't the result that I was expecting here. We may have an error somewhere. Let's see here. We have 1, 10, 0.1. Let's see. Okay, so not exactly sure what happened there. It had to do with my function for our PID transfer function. All that I found was that I changed the order of tau I and tau D, and that gave me the answer I was looking for here. So essentially we have our numerator 0.05 s squared plus 0.5 s plus 0.05. And in denominator, we have s to the fourth power plus s to the third power plus 0.25 s and then plus 0. So I'm going to go ahead and label this as our transfer function in the forward direction of our control loop. And now what we're going to go ahead and do is go back to the whiteboard and derive the servo function for our control loop.
Okay, so here I have drawn out what we're going to call, it's just our feedback control loop here. However, what I've gone ahead and done is condensed it down into GC, GP, and this GM. So essentially what these mean, it's the same idea. We have our set point coming in, we have our comparator here, that then goes into our controller, that then goes into the transfer function for our process. Now this transfer function for our process is what we had just calculated a minute ago in Python. So the Q to Q2, I believe, and then Q2 to H2, when we multiplied those two together, we're just going to condense that and call that our GP, which is the transfer function for our process here. Then we have our H2 coming back. We grab that value here and put it through GM, which is our measurement device here, M for measurement device. And then back up here through our comparator here. So what we can go ahead and do is we can actually look at this by multiplying some of these transfer functions here. So what we have here, this is what we call the forward direction of our feedback control here. So this GC and GP, and then we have our backwards transfer function here, this GM back up to our comparator. But if we take a look here and want to set this up as an equation, what we have here is we have our H2 set point, and then we subtract GM, our measurement transfer function here, multiplied by H2. So H2 set point minus, right, GM times H2. And then from here, what we do is we'll go through our controller here. So we multiply by our controller GC. And then going down after this, we run into our process transfer function. So we multiply by GP. And then this is all equal to H2. So what we can do here is we can do some manipulation to solve for H2 here, to have an equation basically relating this all to H2, because that's what we're ultimately looking to get out of this. So I'm going to go ahead and multiply this through. So H2 set point times GC times GP minus GM H2 GC GP. And this is all equal to H2. Now what I'm going to go ahead and do is just bring this over to the other side. And so if we do that, we'll go ahead and bring H2 out. We'll have a 1 here since we have H2 in there. And then plus GM, GC, GP. And then this will all be equal to H2 set point multiplied by GP and GC. So H2 set point, GC, GP, this is G. Okay, so now what we can do is divide it across here and isolate H2. So I'm actually going to go ahead and do that up here. So I have H2 is equal to we'll take this H2 set point out and have GC, GP all over 1 plus GM, GC, GP. And then this is multiplied by our set point, H2 set point. Okay, so we've gone ahead and isolated H2 here, and essentially what this allows us to do is we can specify any set point here and see how the height in the second tank responds. So this little block of equation here is essentially our transfer function for a process under a feedback control. I've heard that this is also called a servo function. And essentially all that means is that we can specify some set point and then see how the height in the second tank responds. So let me go ahead and erase this here, and we can actually look at this in terms of, I'll break it down in terms of numerator and denominator of the polynomials of our transfer functions here. And that'll make it this type of transfer function under feedback control easier to code into Python. So again, this is our servo function. Let's go ahead and break it down into numerator and denominator of our forward and backward transfer functions in terms of polynomials here. So if you look at this here, just at our servo function here, we have this GC and GP. And if you remember, this is our transfer function in the forward direction. So just to denote the numerator and denominator of those transfer functions, I'm going to call it NF for N, the numerator of the forward direction, and then DF for the denominator of the forward direction. So if we take the same servo function, we'll have NF over DF, right? That's in our numerator. And then in our denominator, we have 1 plus, well, we have our GC and GP again, our transfer function in the forward direction. So same thing, NF over DF. And then we have this multiplied by GM here. But this GM, remember what I said at the beginning is that this is our transfer function in the backwards direction. So I'm going to denote that as a numerator in the backwards direction, so NB, and then DB for denominator in the backwards direction. And this is multiplied here, so we'll go NB, DB. And we can do this, right, because these are all polynomials. We want to be able to do this so that it's easier to code a function in Python. But from here, what we can do is get this, do a common denominator here. So we'll have, we'll still have our same numerator, so NF, DF, and then common denominator we'll have DF, DB, oops, this should be a D, DB, and then plus, let's see here, NF, NB, and this is over DF, DB, right, common denominator. Okay, so from here what I'm going to do is basically multiply our numerator by the reciprocal here. So we'll have NF, DF, and then this will be multiplied by DF, D, where would it be again, DB, and then over DF, DB, plus NF, NB. Okay, and we can just simplify this down a little bit further by canceling out DF. So what our transfer function for our feedback control will look like here is NF DB over DF DB plus NF NB. Okay, and then this is just breaking down the same servo function, again our transfer function for our feedback control in terms of numerator and denominator of our forward and backwards transfer functions. So let's go ahead and head into Python and finish this up by creating a function to be able to calculate our transfer function under a feedback control.
Okay, so let's go ahead and code in our transfer function for our process under feedback control. So let's go ahead and scroll up here, and I guess I can add it in here. I'm going to go ahead and define a transfer function feedback. So our transfer function for the process under feedback control. And what this is going to basically take in is a transfer function in the forward direction and then a transferred function in the backwards direction. Okay. So what I'm going to go ahead and do is essentially kind of unpack our transfer function in the forward direction and transfer function in the backward direction. So we can then go ahead and multiply them as polynomials. So we'll go nf comma df will be our transfer function to polynomial, and that will be our transfer function in the forward direction. And then likewise for the transfer function in the reverse direction, we'll have nb for numerator in the backwards direction, and then db, and that will be our transfer function to polynomial, which will be our transfer function in the backwards direction. Okay, and what we'll want to return is what we had found broken down the numerator and denominators of the transfer functions in terms of polynomials. So we'll go return. In our numerator, we had nf times db, right? And then in our denominator, we had db times df, and then plus nb times nf. So nb times nf. Okay, and then we multiply these, but we need to return them as a transfer function. So we'll go poly to transfer function. Okay, let's go ahead and make sure that that runs. Looks like we have ran everything else. So now that we have our function to be able to calculate our transfer function for our process under feedback control, let's go ahead and test it out. So remember, we had already calculated our transfer function in the forward direction. And for our transfer function in the reverse direction, our measurement device, what we're just going to say is that transfer function is equal to 1 over 1. We're just going to make it simple, just to see if our transfer function under feedback control function works here. So let's go ahead, and I'm going to go transfer function under feedback. And this is going to take in our transfer function in the forward direction, so tf underscore forward. And then our transfer function in the reverse direction would just be 1. So I have transfer function, I will have 1 in the numerator and then 1 in the denominator. Then close that up, put another parentheses, and see if it runs. So tf feedback, let's see here, return. I am getting an error back. Okay, so I found my mistake in returning our polynomial to the transfer function of the feedback control loop. I had these brackets here, and that was just my mental mistake. You don't need brackets here, you just need parentheses around it, and you need to separate your numerator and denominator here. So let's go ahead and run this and see if it works. And it does go ahead and work. So again, this takes in our transfer function in the forward direction, transfer function in the backwards direction, and this is what it returns. So we have 0.05 s squared plus 0.5 s plus 0.05 in the numerator, and then denominator we have s to the third, right, plus 1.05 s squared plus 0.75 s plus 0.05. So now that we have this function to be able to calculate our transfer function under feedback control, this will actually do it for the first part of part 2 for homework 1. There's going to be a second part of part 2, which we'll start off basically using what we have been able to do here to simulate a step response in our control loop. But that will do it for this part of part 2. Thank you for watching.